Somewhere deep in the rainforests of Central Africa, something has been waiting, not thinking, not planning, not alive in any way we would recognize, but waiting nonetheless. A thread of genetic code, wrapped in protein, smaller than anything the human eye can see, drifting through the darkness of an animal host that has carried it for longer than recorded human history. And then one day, contact. A single moment of exposure, a droplet, a touch, a splash of fluid from an infected animal, a bat, perhaps, in a cave or a market, reaching the eyes, the mouth, a small cut in the skin. And the thread enters a new world. The human body. It does not announce itself. It does not immediately destroy. It moves quietly into the tissues, and it begins to do what it has evolved over millions of years to do with terrifying precision. What follows is not a story about outbreaks or headlines or statistics. This is what happens inside, system by system, cell by cell, step by step. This is Ebola. Ebola is a filovirus. The name comes from the Latin word filum, meaning thread, named after the Ebola River in what is now the Democratic Republic of Congo, where it was first identified in 1976. It is a single-stranded RNA virus. Its genetic instructions are written backwards from the way human cells read genetic code. So before it can replicate even once, it must first flip its own genome using an enzyme it carries inside itself. Under an electron microscope, it looks almost elegant, long filamentous, sometimes coiled into the shape of a shepherd's crook. Quiet, patient. There are 5 species that infect humans: Zaire, Sudan, Bundibugyo, Taï Forest, Reston. They are related, but they are not the same. Zaire ebolavirus is the most lethal, responsible for the largest outbreaks in history, including the catastrophic 2014 to 2016 West African epidemic that killed over 11,000 people. Without treatment, Zaire ebolavirus has a case fatality rate of up to 90%. Its outer surface carries one type of protein, the glycoprotein, bristling outward from the viral envelope like hooks. This glycoprotein is everything. It is how the virus finds its targets, forces entry into cells, and directly damages the blood vessels of every organ in the body. It is the virus's master key, and understanding it explains almost everything that follows. Once inside the body, the virus makes a very deliberate first move. It does not attack random cells. It seeks out the sentinels, the macrophages, the monocytes, and the dendritic cells. These are the immune system's frontline scouts, stationed in the tissues, the lymph nodes, the lungs, the liver. Their entire biological purpose is to patrol the body, detect foreign invaders, engulf them, and sound the alarm. The macrophage detects the viral particle. It extends its membrane around it and pulls it inside, a process called endocytosis. The cell believes it has captured and neutralized the threat that it has not. Inside the acidic environment of the membrane pocket, an enzyme called cathepsin cleaves the glycoprotein into a smaller, activated form. This activated glycoprotein binds to a receptor protein called NPC1, embedded in the membrane of the pocket. The viral envelope fuses with the membrane. The viral RNA core slides out into the cytoplasm of the cell. The virus is now inside the very cell that was designed to destroy it, and it begins to replicate. The cell's ribosomes, the molecular machines that build proteins, are commandeered. They stop reading the cell's own instructions and begin reading the virus's instead. 7 viral genes, thousands of copies, new viral particles assembling at the cell membrane and budding off one by one into the surrounding tissue. One infected cell becomes thousands of viral particles, and the infected person feels nothing. This is the incubation period. 2 days. sometimes 21. The person wakes up, goes to work, travels, interacts, cooks food, holds their children, and beneath the surface, in the lymph nodes, in the spleen, in the liver's resident macrophages, the replication continues. Doubling again. The sentinel cells have been turned into factories, and they are seeding every corner of the body. The storm is building, and it is completely invisible. When symptoms finally appear, usually around day 5 to 7, they are almost insultingly ordinary. Fever, headache, fatigue, muscle pain. If you didn't know, if a doctor examining the patient didn't know, you would say flu, malaria, typhoid. In the regions where Ebola circulates, these diseases kill people every day. Early Ebola is clinically indistinguishable from all of them. That is not an accident of nature. It is part of why the virus spreads before it is identified. But inside the body, what is happening is nothing like a flu. The dying macrophages, overwhelmed by replication, disintegrating from the inside out, are releasing enormous quantities of inflammatory signaling molecules into the bloodstream. TNF-alpha, interleukin-6, interleukin-1 beta, MCP-1. These are emergency signals. They are supposed to be targeted alerts, sent to recruit immune cells to a specific site of infection. But when the infection is systemic, when it is in the lymph nodes and the liver and the spleen simultaneously, the signals have no target. They flood the entire system. The immune system is receiving a fire alarm from every room in the building at once. And it is about to get much worse. Here is where Ebola reveals what separates it from almost every other pathogen the human immune system has ever encountered. It does not just evade the immune response. It dismantles it deliberately. Under normal circumstances, an infected macrophage would produce interferons, type I interferons, specifically interferon alpha and interferon beta. These proteins are secreted into the tissue around the infection and travel through the bloodstream, binding to receptors on neighboring cells and switching them into an antiviral state. Hundreds of defensive genes activate. Neighboring cells become hardened against infection. Ebola carries a specific protein, VP35, whose sole function is to stop this from happening. VP35 physically blocks the cellular sensors RIGI and MDA5, the molecular detectors that recognize viral RNA and trigger interferon production. It clamps down on the alarm before it can sound. A second viral protein, VP24, blocks the STAT1 pathway, so that even if interferon does escape into the bloodstream, neighboring cells cannot receive or act on the signal. The warning system is jammed. Cells surrounding the infection receive no alert. They remain fully susceptible, and the dendritic cells, which should be presenting viral fragments to T lymphocytes right now, activating the adaptive immune response, mobilizing the precision strike force of the immune system, are themselves infected, functionally crippled. They cannot pass the activation signal to the T cells waiting for orders. The adaptive immune response, the part of immunity that learns, adapts, and eliminates, is critically delayed. The virus has opened a window, and it is using every second of it. By day 5 to 7, infected monocytes have entered the bloodstream. They are traveling, and because these cells naturally migrate through every organ in the body as part of their surveillance function, the virus is doing something almost architectural in its efficiency. It is using the immune system's own highway network to deliver itself everywhere simultaneously. The liver, the spleen, the kidneys, the adrenal glands, the lymph nodes. Each organ begins receiving infected cells. In the liver, the virus infects hepatocytes, the liver's primary functional cells. As they die, the liver's ability to produce clotting factors deteriorates. Factor 7, Factor X, prothrombin. The proteins that form the scaffolding of blood clots begin to disappear from the bloodstream. The adrenal glands, which regulate blood pressure and the body's cortisol stress response, are infected and begin to fail. The body loses part of its ability to maintain vascular tone. The spleen fills with dying lymphocytes. In fatal cases, measurements have found hundreds of millions of viral RNA copies in a single milliliter of blood. The infection is no longer local. It is everywhere, all at once. Now the virus reveals another weapon. The glycoprotein, the same protein that unlocked entry into cells, also directly attacks the endothelium. The endothelium is the single layer of cells lining every blood vessel in the body. One cell thick, delicate, but absolutely essential. It is the barrier that keeps blood inside the vessels. It regulates pressure. It controls what crosses into the surrounding tissues. The glycoprotein, and a soluble version of it called SGP that is secreted in massive quantities during active infection, hyperactivates endothelial cells and causes them to loosen the tight junctions between them. The vessel walls begin to leak. Fluid, plasma, the liquid component of blood, escapes through the loosened junctions into the surrounding tissues. Organs swell. The circulatory volume drops. Blood pressure begins to fall. The cytokine storm pouring out of the dying macrophages amplifies this further. TNF-alpha and interleukin-6 are among the most potent drivers of vascular permeability known to medicine. The heart works harder, trying to compensate, but there is progressively less blood to pump. The body is losing the pressure that keeps every organ perfused with oxygen. The multi-organ failure that follows is the convergence of everything. The liver failing, unable to produce clotting factors, unable to process toxins accumulating in the blood. The kidneys failing, unable to filter waste, losing the electrolyte balance that keeps the heart and muscles functioning. The adrenal glands failing, unable to maintain cortisol levels or blood pressure regulation. Patients experience relentless vomiting and diarrhea. The fluid losses are catastrophic, several liters per day in severe cases. Combined with the plasma leaking through disintegrating vessel walls, the body is in a converging fluid crisis it cannot resolve on its own. And now, the bleeding. Fewer than half of all Ebola patients develop visible hemorrhage. But when it appears, it is a signal that the coagulation system has essentially collapsed. Here is what is actually happening. The failing liver can no longer replace clotting factors. Simultaneously, the systemic inflammatory cascade has triggered disseminated intravascular coagulation, DAC. In DAC, the clotting system activates uncontrollably throughout the entire body. Microclots form in thousands of small blood vessels simultaneously, in the kidneys, the lungs, the skin, the intestinal wall. This consumes the remaining platelets and clotting factors at a rate the bone marrow and liver cannot replenish. The paradox is devastating. Microclots are blocking blood flow to tissues, contributing directly to organ failure. And yet there are no clotting factors left to seal wounds. Needle puncture sites bleed without stopping. Mucous membranes hemorrhage. Blood appears in vomit, in stool. This is the face of Ebola that the world recognizes. But it is not what kills most patients. Death, in the majority of fatal cases, comes from hypovolemic shock and multi-organ failure. A circulatory system that has lost its volume, its pressure, and its architecture. Organs that have passed the threshold of recovery one by one. Not from bleeding out, from collapsing inward. By day 8 to 12 in severe cases, the patient is in total systemic crisis. Blood pressure critically low, urine output falling, the kidneys shutting down. Tiny hemorrhagic spots appearing beneath the skin where microvasculature has given way. The eyes reddened from conjunctival bleeding. Confusion, agitation, sometimes seizures, from the combined metabolic collapse, the hypoxia, the failing circulation to the brain. Without intensive supportive care, intravenous fluids, electrolyte correction, vasopressors, oxygen, the heart enters shock. And that is the end. But some survive. Studies of survivors from the 2014 to 2016 outbreak revealed a precise biological difference. In survivors, the innate immune response managed to slow viral replication enough in the first days to open a window. In that window, the adaptive immune system mobilized. Neutralizing antibodies against the glycoprotein appeared in the blood around day 6 to 10. They bound to the glycoprotein. They blocked it. Viral replication began to slow. In patients who died, the viral load was dramatically higher. The interferon response had been more completely silenced. The T-cell response, the cytotoxic T-cells that kill infected cells directly, never gained sufficient strength. Sometimes the T-cells themselves were dying in massive numbers through virus-induced programmed cell death. The difference between survival and death came down to one biological race: how fast the virus could replicate, against how fast the immune system could respond. There is one FDA-approved vaccine for Ebola, Ervebo, developed by Merck, approved in 2019. It is built for Zaire ebolavirus. In clinical trials, it demonstrated 100% efficacy in its study population. It is real. It works. For one species. As of 2026, there is an active outbreak caused by Bundibugyo ebolavirus, a different species. No approved vaccine exists for it. 2 approved antibody treatments, Imazeb and Ebanga, also target Zaire only.